Then 2 does not apply. Only for when you have two substitutions on the double bonded carbon. Not one, both carbons that you have the double bond. Okay? So let's see the example over here. So first you're going to be clear from the example, right? So this is, the molecule, right? You have two carbon there, four hydrogen atoms. So ethylene, ethane, right? That's the molecule. So you have one carbon over here, other over here. So if you see the double bonded carbon atoms, you have one substitution that is CH3 for one carbon, and then you have another substitution for another carbon, right? So you don't have the two substitutions in the same carbon. No. You cannot name that if you have that. Okay? So take the double bond. You're going to involve two carbon atoms. So you're going to have one substitution in one carbon, one in the other carbon. So you have total two substitutions, right? That's the condition for this. In any other condition like other than this one, this name doesn't appear there. Okay? So now what you're going to do is take the double bond and then you see whether both substitutions are on the same side or on the opposite side. Okay? If it is on the same side, like this, you have CH3 over here, CH3 over here, right? So this is going to be on the same side of the double bond. So if you have that, this is going to be cis. Okay? If you are on the opposite side, so you have in one side of the double bond, and then the other going to be to the other side of the double bond. The second example, example B, that's going to be trans. That's how we're going to define it. Okay? So for this one, you don't need to view in 3D because the structure is going to be planar. So this is going to be in one plane. So you have the carbon-carbon double bond, and then you're going to have both hydrogen or group on the same plane of the carbon atoms you have, right? So see the plane. If you have on the same side of the double bond, it is cis. If it is opposite, it is trans. Right? It's not hard, right? It's easy one. Okay? So you all are confident on this, right? So now, this is another condition. Okay? So now what if you have more than two now? In the previous slide, you had just two, right? One in one carbon of the double bond and the other in the other carbon of the double bond. So now this name gonna be if you have more than that. So how many maximum substitutions possible you're gonna have? Four, right? So 3 is possible, minimum, but if you see maximum, 4 will be possible, right? So carbonated or valent, you all know that, right? So you have 2 bonds already here. So now you're going to have 2 remaining for this carbon and then 2 for this carbon, right? So you have 1, 2, 3, 4. So maximum you're going to have 4. So for this one, you can have either 3 or 4. Okay? So if you have 2, this doesn't apply. So the previous cis and trans going to be for 2, right? If you have less than 2, just one substitution, even cis trans doesn't appear there. Okay? So for the cis trans, you're going to have 2 substitutions. And then here for EG, you're going to have either 3 or 4. Okay? You can have partial substitutions with the 3 or complete with the 4. Right? So now you're going to do the same thing, same side or the opposite side. Okay? If you have the same side, you're going to call that G. So that's the same side. So before it was 6, right? So G is like a 6. And then if you have the opposite side, it is called E. E is like a trans. Right? So now, here, since you have more than 2, it's going to be confusing. So in which case you're going to call G or E, right? Remember one rule we went before for R and S? You're going to see the atomic number for the atom that has the group in it, right? So you're going to follow that rule. I'm not saying you're going to write R and S over here, but you're going to prioritize the larger or smaller group based on the atomic number. Alright, so that's how you're going to write 1, 2, 3, 4. If you have 3 substitutions, you're going to have 1, 2, and 3. If you have 4 substitutions, then you're going to have 1, 2, 3, and 4. Okay? So you're going to number that based on 1, 2, 3, 4. So 1, 2 going to be like one group. And then 2, 3, 4 going to be like other group. So you can condense that with 1 and 2. So what I mean to that is, let's say you have 1, 2, 3, 4 based on the atomic number, for example, right? So A has the highest atomic number, right? And then 2 has the second highest atomic number, so you're going to call both as a 1 to simplify that. Okay? And then the third highest, fourth highest, for these you're going to call 2. Okay? So now let's see example. Let's see the real example over here. This one. So which one is going to be the highest one? So you have the carbon over here, hydrogen over there, chlorine, bromine. You have 4 atoms there, right? So atomic number of bromine is going to be the highest one, right? So bromine is going to be highest. And then what is going to be the second highest? Chlorine, right? So these 2 are the highest priority atoms. And then third is going to be carbon. And then the fourth is going to be hydrogen. Right? So hydrogen, you don't have any substitute. You have 3 substitution over here. You have 1 bromine, 1 chlorine, 1 carbon. Methyl, ethyl, propyl, whatever you have there. Okay? So now, you're going to see the highest priority atoms in the same side or in the opposite side. So you're going to write number 1 for the highest and second highest. Right? You can think that way. So chlorine and bromine going to be the highest and second highest. So which those 2? Right? So they are in the same side or in the opposite side. Opposite, so this is like a trans, right? So if you don't have carbon over here, if you had hydrogen as an example for this one, if you have hydrogen, what do you write? Trans. You're going to write trans for that because you're going to have only 2 substitutions. If you don't have this, right? If you don't have this alkyl group over here. So now you have alkyl group there. So you have 3 substitutions. So trans doesn't work. So you're going to write E for that. Right? So again, why you write E? You have 3 substitutions, number 1. Okay, that's the criteria. If you have 4, you can write the same thing. Right? 3 or 4. So you can write E or G. So you have the highest and second highest group over here is chlorine and bromine. So pick those two and then see whether you're going to have on the same side or on the opposite side. Right? So the second highest is on the opposite side from the highest atomic number. You can think that way too, whatever way you feel comfortable. Right? So that's why it is E equals to this, right? So now let me modify this a little bit and then let me draw like this. So I have the double bond over here and then I have the chlorine, right? And then I have other groups, let's say R over there, carbon, right? And then I have bromine over here and then I have the hydrogen over here. So if you are given the drawn structure, the structure I drew over here, so what is going to be the name for that? E or G?
C.
Going to be G, right? So again, bromine is going to be number one, that is highest. Chlorine is going to be second highest. So now both highest and the second highest going to be on the same side of the plane of the double bond. So this is going to be G isomer, right? G and then whatever name you have for that compound, name going to go after that, right? So that's how we're going to go. So now, any confusion for cis trans and EG isomers? So cis trans, remember you're going to have only two substitutions there. So you don't need to see atomic number or anything like that. So just see the substituent group in the molecule and then see whether they are on the same side of the double bond or opposite. Same side, you're going to call cis. Opposite, you're going to call trans. So that's easy one, right? So now easy, sometimes a little bit confusing. So the condition is you're going to have more substituent than two. So either 3 or 4. Okay? So now you're going to see the atomic number. So the highest atomic number is going to be number 1, highest priority. Right? And then see the second highest after that. And then see where these two are located. If both highest and second highest are on the same side, you're going to call G. If they are opposite, you're going to call E. Right? Okay. Alright, so now the next thing going to be, if you compare the isomers, which is going to be more stable? So now if you recall alkane, you have the eclipse, stagger, different conformations, right? These are also isomers. So which is going to be more stable? Eclipse or the stagger? I mean, which is going to have the lowest energy? They're going to be the most stable. Stagger, right? So they're going to be the more stable. The same thing over here you're going to apply. So now think, you're going to have cis and trans. If you compare that, which is going to be more stable? Or which is going to have the lower energy if you compare to?
The trans.
Trans, right? So you can see from the picture over here, if you have these cis, what's going to happen is, this is going to be always larger than hydrogen. Right? So it's going to involve many atoms, at least 2, more than 2, or larger number. You're going to have more N for the higher atomic number group, right? So these going to be very close together if they are on the same side. So you're going to have the crowding of the atoms, and then it's going to make less stable. So this gonna wanna go away from the plane. because of the repulsion between the subatomic particles you have, right? So electron repulsion, you can have proton repulsion, right? So that's the reason why it is not happy. If you have the cis conformation, if you have the two substitutions on the same side, the molecule will not be happy. So it's gonna have the higher energy. It's gonna deviate away from that. So gonna be less stable, right? So this is gonna be less stable. And then if you have the trans, so you have one substituent on one side, other in the other side, so they are very far apart. You don't have any interactions between them. So molecule is at lower energy, so gonna be more stable. So without looking the substituent, doesn't matter what molecule you have. If it is asked whether cis is gonna be more stable or trans is gonna be more stable, always choose trans. Okay? Because the larger group is gonna be away from each other. They are two opposite sides of the plane. So that's gonna be the more stable or the less energy isomer. Okay? So that's the one. So now we're going to go slightly towards the reaction. Okay? So now let me recall two terms like nucleophile, electrophile. So how are you going to define that? So let me write Cl minus. If you dissolve HCl in water, you're going to have Cl minus, right? Aqueous. And then you're going to have NH3, for example. Okay? So, what's going to be the name for species like this? It may be ions, it may be molecule, but you can call them electron rich. It's going to have either non-bonded electron pair there or ion, doesn't matter. So both are electron pair. If needed, they can use these electrons to make the bond. So electron rich, right? So what is the name for that? Nucleophile or electrophile? So electrophile is electron lobbing. So it doesn't have electron, so you don't have electron from the other atomic center, right? So this is not electrophile because it already has electron there. That's the nucleophile, okay? So this is called nucleophile. So this type, right, can be molecule, can be ion, don't be confused with that. It can be neutral molecule, say water for example. This is another example. You have two electron pair and oxygen. So it is nucleophile. Okay? It can be electron pair donor. So based on the Lewis base and acid, base is any compound that's gonna donate electron, right? Electron pair donor is base. Electron pair acceptor is acid. That's how we define that, right? So you can also call a nucleophile as Lewis base. The same thing. Okay? So now, once you know that, now let's see the chapter compound in the chapter. So you're gonna have the carbon-carbon double bond, right? So this is the focus, the pi bond. So what's going to be the nature of the pi bond? Do you think it's going to be like a nucleophile or not like a nucleophile, maybe electrophile, electron deficiency? So what do you think? Or I can simplify that. So you're gonna have the carbon, okay? So let me draw this way, the picture like this one. So let's say ethane, the simplest one. So you have two hydrogens over here, and then you have two over here, right? So this is sp2 hybridized, of course. So this is one sp2, this is another sp2, and then this is another sp2. So carbon has three sp2 hybrid orbitals, right? So this is gonna be sigma bond you have, this is gonna be sigma, and then this is gonna be sigma, right? Same gonna be for the other carbon. So you're gonna have one sigma here, here, and then this also gonna count for that. This is common, right? So you have this sigma bonds, right? So carbon is tetravalent. So now you need to have one more bond, which is pi. Okay. So for pi, how are you gonna write it? So you're gonna write like this. You're gonna have the pure p orbital on each, and then you're gonna combine them from this side. This is pi bond. That's the double bond you have. Okay? So now, what do you think? So now from this it is a little bit more clear. So this molecule acts as electron rich or electron poor.
Wouldn't it be electron rich since it's the pure orbital?
Yep, so you have two electrons over here, right? So you have one electron here, one over here. So these two are just sitting in the orbital without bonding with any other atom, right? So essentially, for the carbon, you have one in one orbital, another carbon, you have one in the other orbital, and then they're just overlapping. Okay? So that's the reason why, since you have the side overlap, you don't have the complete overlap of the p orbital. You have just the overlap in the lobe, like a dumbbell shape, just the end lobe. You have overlap in the one end and the other end. In between, you don't have any overlap there. It's not like a sigma bond. You're going to have the strong head-head overlap. So this is weak. That's why pi bond is always weaker than the sigma bond. So whenever you break the bond in the molecule, always pi bond is the one that's going to broken first. And then if you supply more energy than that, then sigma bond is going to be broken after that. You need huge energy to overcome the bonding energy. Right? So now, because of this, these pi electrons, it can make the bond with the other atom if needed. You can think this as a lone pair electron. It's not exactly lone pair. I mean, that's easy to make the bond. Okay? So because of that, it's gonna act like nucleophile. Okay? So whenever you have the electrophile nearby this, so the overlap gonna just disappear over there, and then electrophile gonna make the bond using these two electrons. So the bonding gonna be easy. So that's the origin of the reactions. All reactions are because of that. Doesn't matter what reaction you see, reaction with halogen, reaction with hydrogen, halogen, with water, whatever reactant you have, always the reaction mechanism is going to be the same. So because of the pi bond, that's the center. So that's going to initiate the reaction, and then you're going to have the product based on what another reactant you have there. This is common. So the pi bond initiation is common for all alkene reactions. Okay? So now you know it acts like a nucleophile. So let's see one reaction. Okay? We're gonna add HX on that. So this can be HBr or it can be HCl. So we're gonna focus these two normally. We're gonna focus chlorine and iodine. So we're gonna be very fast, very slow. So this is gonna be right around the reaction speed. So now hydrochloric acid, hydrobromic acid, right? So now here, let's say we're gonna add HBr. So now since you know it is nucleophile, now you can predict the product, what it's gonna be, right? So let me draw the reaction this way. So you have the double bond over here. So H2, H2, the simple one, right? So I'm gonna add HBr on that. Now you're gonna have the product. Okay? So I'm gonna write a different color to just highlight it, how the reaction is gonna be formed. Right? So now, to give the product, you're gonna break the bond in the reactant. You're gonna make the bond to make the product. Right? So this is common for all reactions. So here you're gonna do the same thing. So this bond, double bond, so you're gonna break that. Just the pi. I'm not saying sigma. Sigma is stronger, it doesn't break. Just the pi. Okay? So now you're gonna break that pi bond, and then you're gonna use that electrons to make the bond with one of the hydrogen or bromine. So now you're gonna choose which one. So at the beginning, you're gonna use these two and then make a bond. So now from here, should I point to hydrogen or point to bromine?
Bromine.
Bromine? So now what? So why do you think bromine prefers other than hydrogen?
Bromine has the electron that it can share.
Before that, remember, pi electron act as a nucleophile. After that point, you are sure, right? So to make the bond, what you need? You need electrophile to make the bond with the nucleophile, or you need nucleophile to make the bond with the nucleophile. So here, electron is gonna go this way. So bromine is more electronegative. When you break the bond, both gonna go to the bromine. Hydrogen will not have any electron. So you're gonna have like H like electrophile, or you can say electrophilic center. So it is better to call it. And then bromine gonna be nucleophilic center. Right? So now, since the pi bond is a nucleophilic center, if you choose nucleophile, then how are you going to make the bond? You're going to have the double electron pairs. Okay, so for one bond, you need only one pair. You already have one pair from the pi bond, right? You have two electrons over here. These are the ones you're going to use to make the bond. You're going to choose something that does not have the electron. That is electrophile. You're going to choose that, right? So, or I'm going to write this way. H2C. Actually, let me write with the same color. Oops. So you're going to have the list complete, okay? So make sure you all know this one. Okay? This is the basic. If you know this, you can apply the same general concept for every reaction. It's gonna be easier. So here I'm gonna write the same color. So I'm gonna have H2, and then I'm gonna have C, and then CH2, right? So now when I break the bond, these two electrons, so I'm gonna use these two electrons. So let me go to the different color for that. So these two electrons for the pi bond, okay? So dots. So I'm gonna use a different color. Okay, so this dot. So now, what gonna be the best one? So you have two dots over there. So these two dots are gonna make the bond with the carbon. So now you're gonna have something over here. So what's gonna be? Hydrogen or bromine? Tell me.
Hydrogen.
So I'm gonna write it here, right? Because when you break that, you're gonna have the H plus, Br minus. So the hydrogen is gonna be electrophilic, bromine is gonna be nucleophilic. So you're gonna need the electrophilic to make the bond with the nucleophilic center. Because nucleophile already have the electron there. Okay? So now, these two electrons gonna go over here. So what's gonna be the charge for the other carbon? Loss of electron, right? That means plus or minus? Plus. So I'm gonna write plus over here. Okay, so now you have one plus center which is electrophilic center now. It does not have electron to make the bond. You need to have something that has the electron to make the bond with that center. So do you have any like that?
The bromine with the carbon.
Yep, so see over here. So you have that electron and then you're gonna make the bond over here. So then what I'm gonna write is like this. I have S2, C, and then I have the hydrogen over here, CS2, and then I have the bromine. Let me draw over here right now. So that's the way you're gonna make the bond, okay? So that, and then I'm gonna write the rate over here. So now focus on these two very carefully. Two colors. So the dark color bond comes from the pi electrons. Okay? And the red color bond comes from the SBr bond. Okay? So you have two electrons for the SBr bonding. So these two electrons are gonna make the red bond over there. And the pi electron gonna make the dark color bond over there. So this is the mechanism, the detail. If you don't know this step by step how it's gonna happen, that's how you're gonna explain. Okay? So now you can easily predict the product if you know this mechanism. Okay? Yep.
But how do you know if it's going to be either a cis isomer or a trans?
Yeah. That's the other question. I'm gonna cover that. Yep.
And then I did have another question too. So how do you know where the electrons are going to go, like for the HBr? Is that something you look at through the electronegativity?
Yes, from the less electronegativity to the more electronegativity.
That's where the electrons are headed to.
Yep. That means bromine is going to have more power to pull the spare electrons than the hydrogen. Right? If you see the electronegativity table, you're going to see the larger number for chlorine than hydrogen. That's how I can do it. Alright, so now let's focus on the example given over here. Just like focus on the red box over here. So now it's going to make sense, right? So now you are adding HBr on that. So what are you going to do? You're going to use this pi bond to make the bond with the hydrogen. So that's what you're going to see over here. Right? And then the another bromine you have with the electron in it, that you're gonna see over here. So it's actually bromine in this side, so you're gonna put the hydrogen in the other double bonded carbon. So I'm gonna shift that to the other side. Okay? So I'm gonna shift that over here. The red color. So that's the hydrogen, right? So pi bond gonna be over here, CH, and then the bromine with the electron, bonding electron, gonna be to the other carbon. So that's how you're gonna have the bond. Always. Okay? But the condition, if you don't have anything other than HBr over here. If you put another reagent, then it's gonna be different product. But here right now, the simple one, just with HBr, HCl, without any other reagent added there. Okay? Good? Now you know, right? So if you add HBr, you're gonna put one hydrogen to the one double bonded carbon. You're gonna put the bromine or chlorine to the other double bonded carbon. That's gonna be your product. Right? So why that's gonna be the product? That's the answer. You have the two steps over here. One, you're gonna make the carbocation. So this thing called carbocation, right? Carbocation, carbocation. So that's the step one. You can call the step one is the formation of carbocation. Step two is addition of bromide to the carbocation. You're gonna have the product. So two steps. That's the mechanism, right? So now if this is mechanism, it's gonna make sense. So this is step one, right? This is step one. So which is this one? So you added hydrogen to the carbon, so you're gonna have the carbocation there. And then once you have that, you're gonna add the bromide to the carbocation to have the product, which is step two, is this one. You can add separately if you like. So you start from the carbocation and then Br minus and then product, or you can write in one step. Okay? So this is the mechanism. Right? You can call on your own way, whatever you like. So you're gonna say 5 electrons gonna make a bond with the hydrogen of HBr to make the carbocation, and then the carbocation gonna make a bond with the bromide, or the bromide is a nucleophile that can attack the carbocation center, and then you're gonna make the bond there. Right? Confused? Let me know if you're confused. Good, right? Okay. So now one thing. So if you see this nature over here, the carbocation, so you can have different type of carbon there depending on the substitution. Okay? So you're gonna have C plus with one carbon attached to that, other gonna be hydrogen, right? So you're gonna have one hydrogen there and there. It can be something like that. Or it can be something like this one. So say R1, R2, R double prime, and then one hydrogen like this. Or you can have something like this one. All are without the hydrogen in it. Right? Like that. So here in this example, you have one R and then you have another R. So this example is like this. Okay, so you have the carbon, in which you have two carbon-carbon bond with that, and then you have the one hydrogen. Right? So this is one type. In some cases, you can have without the 2R there, you can have one carbon-carbon bond, or you can have 3 carbon-carbon bond, right? So now, do you think it is familiar? You have seen somewhere like this?
Chiral.
So
Chiral centers.
you have the radical like that,
Oh.
right? You have the 1 electron on the carbon with 1R or 2R or 3R, right? You call 1 degree, 2 degree, 3 degree for that. You're going to do the same thing. Okay? So the first one is 1 degree. Now we don't call a radical for this. 1 degree carbocation. And then you're going to have the 2 degree carbocation. You're going to have the 3 degree carbocation. Okay? So now, applying the same concept of stability for the radical you had before, you're going to apply the same thing over here. So which is going to be more stable? So before you have the same, right? So 3 degree going to be more stable than 2 degree, more stable than 1 degree, same thing. So the more degree you have, going to be more stable, because R can provide the electron to the plus center. It's going to make that happy. So it's going to be more stable. So that's the reason why if you see increasing the stability, so this is going to be the most stable, and then the metal doesn't have R at all, just the hydrogen going to be the least stable. So that's the trend of stability, right? Like radical. It's not different than that. So now your question. You asked me in which side you're gonna go. So this is the one. So now when you draw the product, when you add the nucleophile in particular, so you have the plus on the carbon, this carbon, and then you're gonna have the nucleophile Pr minus as an example. So the p orbital is gonna have 2 lobes, right? So structure is gonna be, your one plane gonna be carbon at the center, and then you have one bond to the other carbon, and then the hydrogen is gonna be over here, other hydrogen is gonna be there. So all sigma bonds gonna be in one plane. Okay? And then the pure P is gonna be one lobe gonna be above the plane, other lobe gonna be below the plane. So now bromine is gonna have 2 choices. So bromine come from the top and then gonna make the bond over here, this side, or it can go below the plane and you're gonna combine to the other side of the lobe, so we're gonna have the bond over here. So based on that, you're gonna have 2 choices to make the bond. And then what's gonna be the probability? 50-50, right? So you're gonna have the equal probability going here and going there. That's why always you're gonna have the mixture. You not have the one sole product there. So 50% is gonna be the product, they're gonna make the bond over here, and the other 50% is gonna be from here. So you're gonna have the mixture. This is called the stereochemistry, the position to make a bond, right? So one is gonna be the R, other gonna be the S, like before, right? So for example, here, let's say bromine is gonna make from the top, okay? So this is the position. So the hydrogen is gonna be on the back as before. They're not rotating the molecule. You have the plane there. So now this is gonna be number 1, and then this is gonna be number 2, and then this is gonna be number 3, right? So you're gonna see the direction clockwise. So R. Okay? So now You have the same molecule. You are not rotating anything. Okay? So now bromine is below the plane. Still it is number 1. So number 2 is going to be this as before. Number 3 is going to be this. So now you're going to go 1, 2, 3. Now it is counterclockwise. So you're going to have the 50% R, 50% S mixer over there. Right? So that's how you're going to have the product. Okay? Alright, so example. So now you can draw this one, right? So you're going to draw the mixer. This is called the racemic mixer. If you have the R and S mixed together, that is called the racemic mixer. So now what do you do? So you're going to do bromine on the top, bromine on the bottom. So one going to be R, 50%, other going to be S, right? So this is going to be R, and then this is going to be S. You're going to have the 50% of that. You're going to have 50% of that. So also called the equal mixing. So for the racemic mixer, you must have equal mixing. If you have the unequal, you don't call this. Okay? Good? Alright. We're gonna stop over here.